Yes, hi guys. Let me describe these important limits, which are very important for the students to remember them, to solve them, to know them. They are the basic formulae as well. They are used as formulae for the next chapters of the differentiation, right? So these are important limits which I have described, which are written down here. Let me explain them one by one or evaluate these limits, which are very important to note down. So let me give the first important limit, which is this one. Limit x tend to 0 sin x upon x, which is equal to 1. This is important limit, one of the important limits which are mostly used by the students for the discussion. They are to be remembered by the student that this is limit. Okay, so let me prove this, that why limit or how limit x tend to 0 sin x upon x is equal to 1. So let me draw a circle of unit limit or unit radius, sorry, this is known as unitary radius. Okay, so let O is the radius of the first center of the circle and let OA is the radius, and now draw, okay, OB, this is OB and OA, so AOB makes an angle x. Here x angle of front, if it is theta angle then it is to be theta. Now in this case it is x. I've taken angle AOB as x, okay, and OA and OB are 1 because OA is 1, OB is 1 radius, so same radii, so this is unitary radius, right, or sorry, unitary circle of radius 1, so OA is equal to 1. Now if I drop a perpendicular OC like this and extend OB up to C, meet AC at C, okay, so this is a right angle triangle OAC. Now join AB as well. Join AB. This is a straight line, sorry. Straight line. So AB. Now in this there are three figures we are obtaining. First is this triangle OAB, one triangle. Then is sector OAB, which is including this curve of the radius, or sorry, of the circle. So there is a sector, right, and then the triangle OAC, this is right angle triangle. So let me take the areas of these three figures. So how the area of triangle, let me take area of triangle, this is area of triangle OAB is less than area of sector OAB, this is OAB sector, right, is less than area of the triangle OAC. This is clear because these areas are obviously or given here, because OAB is the smaller triangle, OAB again the sector is greater than this in area, and OAC is bigger than all than any other area of the triangle. So what are the areas of these triangles? Let me describe them. If I draw a perpendicular from B, this is perpendicular. If I draw perpendicular from B on OA, would the area of the triangle OAB, area of the triangle, any triangle is half base into height. So this is half base OA, half into base OA into this, let me take this as D. BD is the height. Would the BD, this perpendicular upon hypotenuse, base perpendicular upon hypotenuse is sin theta or sin x, here it will be sin x. Alright, so OB into, sorry, this OB into sin x, BD is, let me first write area. So area of the triangle OAB is half OA, the base, into height, let me write here, this is BD, right, is smaller than area of the sector. Area of sector having angle x is equal to x upon 2 pi 360 degree. This is in radians, right? Here x is in radian. Okay. 2 pi is also in 360 degree is radian. Instead of degree I have written 2 pi because it is in radian. So x radian in measurement, right? So x upon 2 pi into area of the circle pi r square, or pi into OA square, because here OA is the radius. OA is the radius, so pi r square, x upon 2 pi, this angle of the sector, divided by total angle 360 degree, which is 2 pi radian, okay, into pi r square, area of the circle. So area of the circle divided by sector, so area of the sector is 10. So pi and pi cancel out. This is x into OA square. OA is the radius of the circle. So is smaller than what is area of this right angle triangle? Area of a right triangle is half base into perpendicular. Base is OA into perpendicular is AC. So half OA into AC. Area of the right angle triangle. Now let me take half OA. What is the BD here? BD is OB into sin x, because let me explain here. BD upon OA is equal to sin x in triangle OBD, because this is side opposite to angle is perpendicular. Perpendicular BD upon OA is sin x, sin theta or sin x. In this case, sin of this angle. So BD therefore equal to OA into sin x. This is OA into sin x multiplied by OA into sin x. Again sin OA whole square OA. Okay, so now let me take the next one. This is x upon 2. X upon 2 into OA whole square. Alright, less than half, again OA into what is AC. Let me find out what is AC. Now AC upon OA, AC upon OA is sin x, sorry, tan x. Y perpendicular upon base is sin x. So OA, let me write here, AC upon OA is equal to tan x. Perpendicular upon base, P upon B is tan x. Okay, so instead of this, sorry, in place of AC, let me write here OA into tan x. This is OA into tan x in this case. So this is OA into tan x. Alright, so AC upon OA in triangle OAC, we have tan x. So in a place of AC, AC equal to OA into tan x. I will replace this. So what we have here, OA square, OA square, OA square. Even if we divide by OA square, they are cancelled out. But OA is 1. That again 1 square, 1 square. Let's write 1 here. 1.2, 1 into 1 into sin x. Less than x by 2 into 1 square. This way less than half 1 square tan x. Okay, so that means half is cancelled out. So sin x less than x less than tan x. Half throughout cancelled out is half. If I divide by half, so this is x only, tan x. If I divide by sin x, so x upon sin x, divide by sin x, we will this imply that 1 is less than x upon sin x, divided by sin x. This is 1 upon cos x. 1 upon cos x. So in case when x tends to 0, cos 0 is 1. So x upon sin x is lying between 1 and 1. So in limiting position, that is in the numerator. Okay, so in the limiting position, if I apply the limits, the limit x tends to 0, x upon sin x equal to limit x tends to 0. Okay, 1 upon cos x, and this is equal to 1. That means this limit x tends to 0, 1 upon cos 0 is 1, this is 1. That means x upon sin x is lying between is greater than 1 less than 1. That means limiting position x tends to 0 in the limit x tends to 0, sin x upon x equal to 1. Proved. So this is how we prove this sin x upon x by taking the areas of this unitary circle, right, or circle with radius. Now this is a very important question which is to be remembered by the students, that limit x to 0 sin x upon x is 1. This is the first question which I have explained here. Evaluate. The first limit is evaluated. Now let me take the next limit, second one. Second question is also very important. Limit x tends to 0. A raised power x minus 1 upon x is equal to log of a to the base a. Okay. Now if I explain a raised power x instead of a raised power x, if I write it as e raised power x into log of a to the base e, ax can be explained like this, is, or you can write it as log of e to the base e whole power x, the same thing, and this log of e log of a to the base e is equal to a raised power x. A raised power x can be written like this. Okay, so instead of this, let me write here limit x tends to, this implies that a raised power x minus 1 from x. I'm taking right hand side here, right hand side, sorry, left hand side, I'm taking left hand side. Let me prove this left hand side is equal to how much? Limit x tends to 0. Instead of ax, or in place of a raised power x, I have to substitute this. This is e raised power x, is x log of a to the base e, right, minus 1 divided by x. Now what is the value of e raised power x, or any number? Let me put here. We know that e raised power x is explained by 1 plus x square upon factorial plus x cube upon factorial 3 plus x4 upon factorial 5, sorry 4, and so on. Okay. Similarly, if I explain this e raised power x log of a, this is e raised power whatever, that is to be placed in place of x. If I replace this expression of e raised power x, in place of x, I have to substitute x log of e. Okay, so we can obtain by this expression of e raised power x. Okay, so limit x tends to 0. In place of this, I have to substitute x in log of ae plus x square upon factorial 2 log of a to the base e whole square plus x cube upon factorial 3 log of a to the base e whole 2 plus and so on, and this is minus 1 divided by x. Last minus 1 and this plus 1 cancel off. Okay, so every term of this question is to be divided, of this expression is to be divided by x. So we will obtain, sorry, limit x tends to 0. This is nothing but log of a to the base e plus, if I take here, it is x upon factorial 2 only, because x1 cancelled out by dividing this, log of a to the base e whole square plus and so on. All terms will contain here x square will come up and so on. Okay, so all the terms when x tends to 0 will become 0. Only log of a to the base e is left over. This is the answer, log of a to the base e. Log of a to the base e. This is proved. Second question is proved. Now what is the third one? Let me next take the next third one. So the third question is okay, this is the next one. Third question, let me take limit x tends to infinity when it is 1 upon x tends to infinity when it is x tends to 0. This is to be remembered by the student, that when 1 upon x is there, then limit is infinity. When x is there, then limit is x tends to 0, and both are similar type. Okay, they are corollary of each other. say that they are corollary of each other. Okay, they are similar types. Now let me take first one. Limit x tend to infinity. This is 1 plus 1 on x whole power x. Okay, which is equal to e. Let me take right hand side, sorry, left hand side. In left hand side is this one. Limit x tend to infinity 1 plus 1 upon x whole power x. Right. If I take this as y, this whole expression get limit x tend to infinity y equal to limit x tend to infinity 1 plus 1 upon x. If I write like this, or y equal to this value. Okay, to take log of this whole, log of y equal to log of 1 plus 1 upon x. Okay, or x, because log of n raised power n is n log n. X will come in the multiplication. X log 1 plus 1 upon x. Right. Now express this in terms of log. Then apply the limits. Okay, if x tend to infinity, naturally 1 upon x tend to 0 then, because this is 1 upon x, x infinity means 1 upon 0, it will come up. So 1 upon x will tend to 0. If I write here x log of this, if I explain this 1 plus 1 upon x whole power x, in this case here, this will be x into, now what is the expression of log of x? Now log of x, 1 plus x, log 1 plus x is explained or is expressed as x minus x square upon 2 plus x cube upon 3 minus x4 upon 4 and so on, plus and so on. This is expression of log of 1 plus x, right? Expression of log of 1 plus x is x minus x square upon, like this. Similarly, if I explain this, and then put the limits here. So in the limiting position, limit x tend to infinity. Here also limit x tend to infinity. Let me write here limit x tend to infinity. The same question I have explained in terms of log. So okay, so this is equal to limit x tend to infinity or 1 upon x tend to 0. If I write 1 upon x tend to 0, the same thing is there. 1 upon x tend to 0 or x tend to infinity. Right. This is x into, okay. So x into, this is 1 upon x, first term comes minus 1 upon x whole square into 2 into x square plus 1 upon x cube into 3 minus and so on. Okay, so if I divide by x, we will get, and then x tend to 1 upon x tend to 0. The remaining terms will contain 1 upon x. So let me write here limit 1 upon x tend to 0. This is 1 minus 1 upon 2 into x plus 1 upon 3 into x square and minus and so on. Every term other than 1 will contain 1 upon x, 1 upon x. 1 upon x tend to 0. By substitute, this will be equal to 1. Okay, in the limiting position. So therefore, y is equal to log of y is log of y is equal to 1. We have obtained this limit 1 upon x tend to 0. Okay, so therefore y is equal to e raised power 1. That means okay, log of y is equal to e raised power 1. That means e only. Here also it is, therefore y is equal to 1. Log is removed. Then this is e raised power 1. The log of y equal to 1. That means y is equal to e. So this is how the second is also proved. This one. So third one, sorry. Now fourth one, let me take the fourth one. The fourth question is of the corollary type of the three. So here it is fourth. Let me talk about limit x tends to 0, okay, infinity. Now this is 1 plus x whole power 1 upon x. We have to prove that this is equal to, right? So how it is easy. Now let me take only left hand side, because these questions are given here, so don't waste time. Now 1 plus x 1 upon x. Now if I explain this, okay, so this is to be explained x tends to 1. If I express this by binomial theorem, this is to be explained by binomial theorem, because 1 upon x power is there. Instead of n we have 1 upon x. Okay. So we will have this by expressing this by binomial theorem. Let me take, or if I take by again the log, let me take y equal to log, explained by the same method. So that y equal to 1 plus x whole power 1 upon x. So take the log of both sides. Log of y is equal to 1 upon x into log of 1 plus x. Okay. So when in the limiting position, limit x tends to 0 log of y is equal to limit x tends to 0 1 upon x into log y, log 1 plus x, as I just have expressed, that 1 plus log of 1 plus x is x minus x square upon 2 plus x cube upon 3 minus x 4 upon 4 and so on, plus and so on. Okay, so if I divide by x, the whole term, it will become 1. The first term will be 1, limit x tends to 0, and the second will x upon 2 plus x square upon 3, plus every term will contain x up to this was, okay, and this terms on the only one will left over. Again, 1 is there. Therefore, in the limiting position, the y is 1, limit x tends to 0. Therefore, y is equal to e raised to power 1. That means sorry, so y is equal to e. If I remove the log y is equal to 1, so y is equal to e. That means y is equal to e raised to power 1. That means e only. So this is also proved. Okay. So I taking the log of both the sides by assuming 1 plus x or 1 plus 1 plus x y, we can solve both the questions. They are corollary of each other. These questions are very important. Okay, so third and fourth one. Now let me take the next question. Now in this case, the fifth one. The fifth question is limit x tends to a x raised power n minus e raised power n divided by x minus a. Okay, which we have to prove that this is equal to n raised power n minus 1. Okay, so let me prove this. Let me take the left hand side only. So how do you have to prove this? So this, let me substitute in place of x. Let me write here. So this is x into a plus h. If I write in place of x, put or substitute x tend to a plus h, or in place of a plus h, where h tends to 0. This implies that h tends to 0. So instead of x tends to a, we write x equal to a plus h, where h tends to 0. X tends to a. Instead of this, we write a plus h. Replace x by a plus h, and h tends to 0. So right here, limit h tends to 0. This is a plus h whole power n minus a raised power n divided by a plus h minus a or a and a cancel out. A and a cancel out. In the denominator we have only h. This is we obtained limit h tends to 0. Okay. A plus h whole power n minus a raised power n divided by h. Here h is 0. Now again, a plus h whole power n is to be expressed by with the help of binomial theorem. So the binomial expression of this question is h tends to 0. A n, right? A plus h whole power n This is binomial expression. I'll note down the formula of binomial curve. Okay, in the next lecture or maybe after the questions are solved. Okay, so what is binomial expression of a plus h whole power n, a raised power n plus n into a raised power n minus 1 into h, right? Plus n into n minus 1 upon factorial 2. Here it was factorial 1 only, into a raised power n minus 2 into h square plus and so on. Last step is minus a raised power n left over divided by h. If we see a raised power n, a raised power minus a raised power n cancelled out, and if I divide this whole by h, only the first term will be free from h, other terms will have h. This is h only, next term h square and so on. All terms will be the questions of this. Okay, so limit when h tends to 0 divided by n h, so we get limit h tends to 0, it is n a raised power n minus 1, which is free from h. Next term will contain h. This n into n minus 1 upon factorial 2 into a raised power n minus 2 into h plus every term will contain h. So this in this way, if h tends to 0, the every term other than this will become 0. So we will have in the limiting position when h tends to 0 and a raised power n minus 1 is the answer which we obtain here. Okay, the answer is the same. In this way, the question is solved. So this formula is also, this is used as a formula. So these are used as formula or questions if are coming, we can solve them in this way. Now, next question, this one. Sixth one, let me take sixth question. This is limit x tends to 0. Limit x tends to 0. This is 1 plus x whole power n minus 1. This is 1 upon x. We have to prove that this is equal to this is big. So, on the left hand side, now again explain this or express this with the help of binomial curve. What is that binomial curve? So, limit x tends to 0, 1 plus x whole power n minus 1 upon x, right, is equal to, if I express this with the help of binomial curve, we will get 1 plus, because 1 raised power n is 1. So 1 plus n into x plus n x square upon factorial 2. Alright, plus n into n minus 1. Because power is n into n minus 1 into x square into x square upon factorial 2 plus n into n minus 1 n minus 2 upon factorial 3 into x cube plus and so on divided by x. And here it was minus 1. Last term was minus 1. So minus 1 and plus 1 cancelled out. So we obtain the terms which are okay. Which will have x other than this number, because x will be cancelled out from the first term only. B, when in the limited position when x tends to 0, every term will contain. Let me write it again. Limit x tends to 0. This is n plus n into n minus 1 upon factorial 2 into 1x, and x is power 1 only, plus other terms will contain x, x into the terms containing power of x, powers of x. Okay, so when x tends to 0, every term will be 0. This also will be 0. Only n will be left over. This is n. So this is solved. Now let me take the next question. So these 10 questions today are. And any other important questions which are left over, I've seen that they are coming in the exams. I'll solve them also in the next lecture. Okay. After that, I'll take the continuity, because continuity is very important before discussing the differentiation of the starting differentiation proper way. Okay, from fundamental questions of differentiation. Now let me take the seventh question. Now in the seventh question we have to solve, because this question has come up in one of the exams of BTech or somewhere in the graduation. Okay, so I've seen this question. So 10x divided by x, okay, is equal to 1 we have to prove. So let me take the first question. So write it as limit x tend to 0. This is sin x upon x into 1 upon cos x, because 10x is sin x upon cos x. So I have written down this as sin x upon x cos x. So this is equal to, I'm taking left hand side again to solve it. So 10x has been written as sin x upon cos x and 1 upon x as it is. Now sin x upon x, when limit x tend to 0, if I apply limit on both these questions separately, so sin x upon x divided by x into limit 1 upon limit x tend to 0 into cos x, this is equal to 1 upon 1 is 1 into 1 upon 1, that means 1. This is also proved. So seventh question is proved. Okay. So we have to apply the same limit which I described in the first one, sin x upon x is 1. That limit has been used in this. So in this way we use these formulas wherever they are coming. Okay. Next question, eighth one. That will be the eighth question. So limit x tend to 0. Limit x tend to 0, e raised power x minus b raised power x divided by x. We have to prove that this is equal to log of e a by b. Alright. Again, express these a raised power x, b raised power x in the form of exponent or exponential form. So if I write then limit x tend to 0, this is e raised power x log of a to the base e minus e raised power x log of b to the base e divided by x. So I have expressed these e raised power x and b raised power x in this exponential form. Now, okay, express them, or okay, now expressing them in the terms of exponential terms. You know that e raised power x is what? So in the same way, limit x tend to 0. If I express this is, first term is 1 plus, okay, 1 plus x e raised power, log of